Now this problem is getting even trickier. Same kind of concept, but it's just getting a little bit harder every time. So here again, we have three reactions that we're looking at. And the first thing that it's asking you is yes or no, is this even a redox reaction? And if it is a redox reaction, then you have to identify the reducing agent and the oxidizing agent, which is not the same as identifying which reactant is being reduced and which reactant is being oxidized. So let's first talk about how do you go about identifying if it is a redox reaction. What you're going to look for is anything that has a change to an oxidation number. Anything with an oxidation number change. If you can find one, then yes, it's a redox reaction. You only have to find one. A non-redox reaction is going to be one where none of the oxidation numbers change. None at all. So if you have no oxidation number change, then it's not redox. Now, again, you might be thinking, oh my gosh, I'm going to have to assign oxidation number to every single atom. And that's actually not true. Again, I'm going to show you shortcuts on how you can get around having to identify every single oxidation number. And we're going to start with the easiest one, which is the one in the middle right here. So when I'm looking at these and I'm trying to decide if it's an oxidation, if it's a redox reaction or not, just like a yes or no, the first thing that I want to see, the easiest way that I'm going to figure this out, I want to see just an atomic elemental metal like tin, like we have. That's going to be something that's really easy for us to work with because we know without thinking, we know that its oxidation number is 0. Anytime you see a metal all by itself, uncharged, its oxidation number is 0. So then what I'm going to do is go to the other side of the equation and I'm going to look at tin again and I'm going to assign the oxidation number for this tin. This tin is with 4 chlorines. Chlorine as an ion is a very common ion with a -1 charge. So all 4 of those chlorines together have a total oxidation number of -4, which means that this tin in this compound has an oxidation number of +4. So since I found something that had a change to its oxidation number, that means that yes, this reaction is a redox reaction. I only have to find one thing. So then the next thing that I need to figure out is what is the reducing agent, what is the oxidizing agent? So let's do a refresher on what that actually means too. What does it mean to be a reducing agent? What does it mean to be an oxidizing agent? The reducing agent is the thing that gets oxidized It gets its name, we call it the reducing agent, because it causes the other reactant to be reduced. And likewise, the oxidizing agent is the thing that gets reduced and also causes the other reactant to be oxidized. The key that you're looking for here is the word agent. The oxidizing agent is the thing that causes the oxidation, and the reducing agent is the thing that causes the reduction. So to find the reducing agent, we need to find what gets oxidized. We've already assigned oxidation numbers to the tin, so let's just focus on tin. What's going on here? We're going up from 0 to a +4. We're increasing in oxidation number, which means that tin is being oxidized. If tin is being oxidized, it is causing the other reactant to be reduced. So tin is the reducing agent. This is tricky because we're like flipping these words around totally. The oxidizing agent is the thing that gets reduced. What is getting reduced? Now, you might think, oh, we've got to figure these numbers out. But you actually don't, because it has to be chlorine. It has to be Cl2. There's only 2 reactants, and we've already assigned one of them. So if you wanted to, you could double check. Is this actually being reduced? Cl2, that's pure elemental chlorine. That's got an oxidation number of 0. And we said over here in SnCl4, that's an oxidation number of -1. 0 going down to -1, that is a reduction. So yeah, it works. But this is a lot like acid-base chemistry. Once you define one of them, you automatically know what the other one is. So let's look at the last one, because I think that the last one is the next easiest one that we have. And so again, here's my strategy. First thing I'm going to tackle is the first question. Is this even a redox reaction, yes or no? And in order to answer that question, I'm looking for any one single thing that's had an oxidation number change. And the easiest thing for me is to find a pure metal, elemental pure metal, like I have iron right here, and I know that it's a 0. And so now I'm going to look for iron on the product side. Here it is. And I'm going to assign its oxidation number as a product. Iron is with these 3 chlorines. Chlorine has a charge of -1. There are 3 of them for a total of -3. So that means this iron has an oxidation number of +3 and a charge of +3. And so since iron's oxidation number has changed, that means that yes, this is a redox reaction. Anything, it only takes one thing to have a change in oxidation number, and you know, yes, that's redox. So since we know that it's a redox reaction, now we have to decide what the reducing agent is and what the oxidizing agent is. Remember, the reducing agent is the thing that gets oxidized, and the oxidizing agent is the thing that gets reduced. So what's going on with iron? We've already focused on iron. We are going from a 0 up to a +3. That's an oxidation. It's an increase. The reducing agent is the one that gets oxidized. So iron is our reducing agent. And once we figure out one of them, we immediately know the other one. Nickel has to be the thing that gets reduced. One will always get oxidized and the other one will always get reduced. So now we're ready for the last one. And this one is the trickiest one. When I'm looking at the top one here, this one is the hardest one. And the reason that it's hardest is that there isn't a single pure elemental thing for us to focus on, like tin or iron. Every atom is part of a compound, which is going to make it trickier. And that's going to require us to think quite a bit more. Well, we have hydrogens in here, and unless it's all by itself or in some sort of weird thing like H-, unless it's in a weird situation, hydrogen is always +1. So we know that hydrogen is not changing. And we also have oxygens, and oxygen is another one that's consistent. It's always going to be a -2 unless we have some sort of weird thing like O2 or O22-, which we don't have here. We just have a whole bunch of regular oxygen. So we know that the hydrogens and the oxygens are not being having their oxidation numbers change. So that means we need to focus on carbon. Is anything exciting happening to carbon at all? It's our last hope, right? So let's focus on the CO2 for starters. We have 2 oxygen atoms. Each one is a -2. That's a total of -4. So this carbon right here is a +4. So carbon is starting as a +4. And what is it ending with out here? I'm going to make some more room up here. HCO3-. So we have 1 hydrogen, which is +1. So that guy is a +1. We don't know what our carbon is. We have 3 oxygens that are a -2. That's a -6. We have 1 carbon. We don't know what it is. So we don't know what this oxidation number is. And all of these together need to add up to -1, which is the charge of the HCO3 minus ion. So +1 minus 6 plus what is going to equal -1? It looks like this has to be a +4. No change. So carbon also does not change. Hydrogen doesn't change. Oxygen doesn't change. This is not a redox reaction. And since it's not a redox reaction, we don't need to fill out anything in those boxes.